Have you ever stopped to wonder whether the world you see around you is the whole story? Imagine that every star, every particle, every moment of time is not the fundamental reality, but rather the projection of information stored on a distant cosmic screen. This is the heart of the holographic principle, a radical idea born out of black hole physics that suggests our three-dimensional universe, and even the flow of time, might emerge from data encoded on a two-dimensional boundary. Think of the hologram on your credit card. When you hold it up to the light, a flat film reveals a shimmering three-dimensional image. The shape, depth, and all the detail you see exist only because information is cleverly stored in patterns on that thin surface. Now amplify that concept to cosmic proportions. What if the entire volume of space, from the tiniest atom to the farthest galaxy, is a kind of celestial hologram? All the information about every object and every interaction could be written on a distant boundary, like characters on a two-dimensional screen, that when read in just the right way, paint the reality we experience. The story began in the 1970s with Jacob Bekenstein and Stephen Hawking. They discovered that black holes, those mysterious cosmic vacuum cleaners, don't hide information behind their event horizons in the way you'd expect. Instead of an entropy, a measure of hidden information, scaling with the volume inside the black hole, it scales with the surface area of the horizon. In simpler terms, the information about everything that fell into the black hole is encoded on its two-dimensional surface. This startling deviation from ordinary thermodynamics hinted at a deeper bookkeeping system in nature. Maybe the degrees of freedom in any region of space are fundamentally limited by its boundary. Building on this, Gerard 't Hooft proposed in the early 1990s that any quantum theory of gravity must obey an area bound on information, a principle he called dimensional reduction. Leonard Susskind then coined the phrase holographic principle and showed how string theory naturally realizes this idea. He argued that gravity in a volume of space could be exactly equivalent to a non-gravitational theory on its boundary, a direct cosmic translation between dimensions. The definitive breakthrough came in 1997 when Juan Maldacena introduced the AD-CFT correspondence. In his landmark proposal, a five-dimensional universe with gravity, dubbed anti-de Sitter space, is fully equivalent to a four-dimensional quantum field theory without gravity on its boundary. Two seemingly different worlds, one with gravity and curvature, the other a flat playground of particles and forces, turn out to be the same story told in different languages. This duality means that complex gravitational problems can be transformed into more manageable calculations in a lower dimensional setting, and vice versa. Underpinning all of this is the famous Bekenstein-Hawking entropy formula. The entropy of a black hole equals 1/4 of its horizon area in Planck units. This area law scaling implies a universal information bound 1 bit per tiny Planck area on a surface. Push the information density above that limit, and the energy you inject would collapse into a new black hole, sealing away the extra data behind an event horizon. Mathematicians and physicists have built a precise dictionary between bulk gravity and boundary field theories. They equate partition functions. The sum over all possible histories in the boundary theory matches the gravitational path integral in the bulk. One of the most elegant results is the Ryu-Takayanagi formula, which calculates the entanglement entropy of a region on the boundary by finding the minimal surface area in the bulk that spans that region. In other words, quantum entanglement and space-time geometry are two sides of the same holographic coin, while direct experimental confirmation remains elusive, clever tests have been proposed. In 2017, researchers examined the cosmic microwave background, the afterglow of the Big Bang, for patterns predicted by holographic cosmology models. Remarkably, certain non-geometric, holographic explanations matched observations as well as the standard inflationary picture. On Earth, Fermilab's Holometer experiment used twin laser interferometers to search for holographic noise, the jitter that would arise if space-time itself were pixelated at the Planck scale. No such signal surfaced, ruling out one simple pixelation model, but leaving the broader principle intact. Leading voices in physics see holography as a profound clue to the nature of reality. Leonard Susskind believes it lies at the core of quantum gravity and has employed it to resolve paradoxes around black hole information. Stephen Hawking, once skeptical, later embraced holographic ideas in his work on the origin of the universe, imagining a timeless two-dimensional screen of entangled qubits birthing spacetime and the flow of time itself. Juan Maldacena treats holography as a powerful mathematical tool, even if he regards its literal application to our universe as an open question. Eric Verlinde has taken it further, proposing that gravity emerges as an entropic force from microscopic holographic surfaces, potentially explaining galactic mysteries without invoking dark matter. Philosophically, the holographic principle upends our assumptions. It invites us to question whether space is fundamental or an emergent illusion. Are we inhabitants of a cosmic Plato's cave, mistaking shadows on a wall for true reality? Some draw parallels with the simulation hypothesis. Perhaps our universe is the output of computations run on a distant quantum processor. Others point out that even our own brains construct a three-dimensional experience from two-dimensional retinal images. So why shouldn't nature do something similar at its deepest level? Applications of holography extend across cosmology, quantum gravity, and condensed matter physics. In early universe models, a holographic phase could replace cosmic inflation. In black hole physics, AD-CFT demonstrates explicitly how evaporation preserves information, avoiding paradox. In materials science, holographic dualities provide novel insights into strongly interacting systems like exotic superconductors. Yet important puzzles remain. Our cosmos has a positive cosmological constant, not the negative curvature of RDS space, so an exact holographic dual for our universe is still missing. There is no general proof that holography applies in all contexts. Exotic theoretical constructions, like Wheeler's bags of gold, threaten to violate the entropy bound. And without a clear smoking gun prediction, critics warn that the holographic principle may be more metaphor than testable law. Nevertheless, the holographic principle has reshaped the frontier of theoretical physics. It has forged new connections between geometry, quantum information, and gravity, suggesting that the very fabric of space-time emerges from patterns of entanglement and boundary data. Whether or not our universe truly is a hologram, the insights born from this idea continue to drive progress toward a quantum theory of gravity, offering a tantalizing glimpse of a deeper reality where information reigns supreme over space and time. We hope this exploration has enriched your understanding of these profound scientific concepts. For more in-depth analysis of complex phenomena, consider subscribing to our channel. Until our next examination of the natural world.